In this section, we're going to take a look at the graphs of the tangent, the cotangent, the secant, and the cosecant functions.
So let's begin with a few values. We can take values of theta and substitute into the tangent of theta to give ourselves some values to graph. Now, before we do that, note that there are going to be some values that we cannot use. Going back to the unit circle, we remember that the tangent of the angle theta is given by the sine of the angle theta, meaning these y values here, divided by the cosine of the angle theta, meaning these x values here. And you'll notice right here that at this point and at this point, we have that theta is, the cosine of theta is equal to 0. So sine of theta divided by cosine of theta is 1 over 0, which is undefined. Likewise here, we have negative 1 over 0, which would be undefined. So when we go through and substitute in values, note that pi over 2 is not a valid substitution. We won't be able to do that. Likewise, 3 pi over 2 would not be valid. Now keep in mind, if you go around the circle, you end up back here again eventually. So when we say pi over 2 is not a valid substitution, going all the way around would give you 5 pi over 2, which would also not be a valid substitution. If you go all the way around, you do that again and again and again. And if you go backwards, I could say negative pi over 2. I could say negative 3 pi over 2. It doesn't matter what angle I choose to use. If it's coterminal to either pi over 2 or 3 pi over 2, tangent will be undefined. So let's keep that in mind. We can't use pi over 2, 3 pi over 2, and so forth. So when we do that, note that pi over 2 and negative pi over 2 won't be used. Again, negative pi over 2 because positive 3 pi over 2 is the same as negative pi over 2. So let's keep that in mind. Those won't be used. But we can use other values. So for example, we can say pi over 6. Well, actually, let's just start off with 0. So tangent of theta is sine of theta over cosine of theta. Okay, well, if here's 0, that's sine of theta over cosine of theta. 0 over 1, which is just 0. Right? 0 can't be a denominator, but it's okay if it's a numerator. So I have a point 0, 0. Okay, there we go. Let's use another point here. Let's say pi over 6. Okay, well, pi over 6, if that's my angle, the tangent will be the sine divided by the cosine, 1 over 2 divided by root 3 over 2, 1 over 2 divided by root 3 over 2. Here the 2's divide away, and we're left with 1 over root 3, like that. Here we can rationalize this, but here, since we're trying to graph it, we might just be better off with a decimal approximation. If we needed the exact value, it would be this, which we could then rationalize. But since I'm trying to graph this, let me just see what it looks like as a decimal. That's about 0.37. About 0.57, give or take. Yeah. So here, if your angle is pi over 6, you get approximately 0.57. Okay, so about halfway up right here. A little bit more than halfway up. Here, that's 0. That's pi over 2. So halfway in between is pi over 4. All right, so let's use pi over 4. Let's see what happens there. Notice that at pi over 4, the sine and the cosine are exactly the same. So sine of theta over cosine of theta, well, that's just going to be 1. A number divided into itself is exactly the number 1. So if your theta is equal to pi over 4, then the tangent of theta is just equal to 1. So there's my point. Let's do another one. Let's say pi over 3, like this. And pi over 3, if I take the sine of pi over 3, that's root 3 over 2, divided by the cosine of pi over 3, root 3 over 2, divided by 1 over 2. Okay, well, these 2's divide away, and we're left with root 3 over 1, or in other words, just root 3. And root 3 is about 1.7, give or take. So right here, that's 1.3, a little bit less than 1.2. And my tangent of that theta will be about 1.7. Not quite all the way to 2, something like that. All right? All right, now, note that I can plug in some negative values here. There's nothing wrong with that. You say, well, why don't I keep going? Well, the problem is I can't keep going much further because at pi over 2, it'll be undefined. You say, okay, well, can you, so what happens when you get to pi over 2? Well, nothing. By definition, if it's undefined, that means it doesn't exist on the graph. But notice that as you get closer to pi over 2, your graph continues to grow up and up and up. If you follow this pattern, it'll start going up this way. But of course, we know it can't ever have a theta value of pi over 2, so that means that we have this line that we need to avoid. Okay, so we have a vertical line that your graph can't touch, but which is going to continue to grow alongside of. Thinking back to college algebra, what was that called? That's called a vertical asymptote. Here, the tangent function has a vertical asymptote at pi over 2. You'll note that that's where it's undefined. We said a moment ago that negative pi over 2, your graph will also be undefined when theta is equal to negative pi over 2. Your tangent will be undefined there. So here we'll have another vertical asymptote at negative pi over 2. If I substitute in some numbers between here and here, I can fill in a few more points. Let me just use negative values. Negative pi over 6. All right, well, negative pi over 6, that would be going, okay, that's pi over 6, but negative would be in the opposite direction. So that's this point over here. All right, so the cosine of negative pi over 6, that's the sine of negative pi over 6. Notice those are the same numbers, except that here, the sine of negative pi over 6 is negative 1/2 as opposed to positive 1/2. So that'll be the same number that we had up here, except this number here will be a negative, which will make this number a negative. So I have negative 1/2 divided by root 3 over 2. Only the top is negative. The 2's divide out, and we're left with negative 1 over root 3. So it's that same number, but now going in the opposite direction. So that's about right here. If we use negative pi over 4, the sine and cosine of negative pi over 4 are the same as these, except that now, because this is negative, the sine value, the numerator, will be negative. So negative root 2 over 2 divided by positive root 2 over 2. Oh, well, that's negative 1. Okay, so if my theta value is negative pi over 4, my tangent of theta is negative 1. And if I use negative pi over 3, I get the same numbers I have here, except it'll be negative. Negative root 3 over 2 divided by 1/2. The 2's divide away, and I'm left with negative root 3 over 1, which is just negative root 3. So here, if we connect all of these values, connect all these dots, we start to get a pattern. Note again, these two lines are vertical asymptotes. Your graph won't ever touch them. So your graph looks something like this. And there we go. This is the central period of the tangent function. Just like sine and cosine, tangent is periodic. It does keep on going forever and ever and ever. And here we can continue to graph further periods of it. If you just take this and basically copy and paste, put this one here, you can have more copies of this function. So here, the period length from negative pi over 2 to positive pi over 2, that distance is pi. So if you add that same distance again, if you take pi over 2 and add another pi, that's 3 pi over 2. So that would be location of another vertical asymptote. Note that halfway in between the vertical asymptotes, I am at the axis. Okay, so halfway between these two, I'm at the axis. If I go halfway between this midpoint and this endpoint, the tangent is 1. Okay, so halfway between here and here, the tangent will be 1. Over here, halfway between the midpoint and the beginning, a quarter of the way in, my tangent is negative 1. Okay, so down here, and I could just repeat that same pattern over and over and over again. I could do that again and again and again. This is another period of the tangent function. So just like with sine and cosine, we define this one, the one that touches theta equals to 0. We go ahead and define this one as the central period. All right. Note that the sine and cosine functions had 5 points of interest, a beginning, an end, a midpoint, a quarter point, and a 3/4 point. Here we have 3 points of interest. We have a midpoint, 1/4, and 3/4 of the way through. And here, tangents don't have a beginning or an end point. They go on forever. But we have asymptotes instead of beginning and ending points. So there are still 5 pieces of information that interest us. Left asymptote, right asymptote, quarter point, midpoint, 3/4 point. Okay? Just like that. We can do the same thing for the cotangent function. And the cotangent function can be found exactly the same way. Note that, just like the tangent, the cotangent will have asymptotes because the cotangent can be defined as the cosine of the angle theta divided by the sine of the angle theta. But looking on the unit circle, there are places where the sine of the angle theta is going to be 0. Namely, if theta is equal to 0, then the cotangent of theta would be 1 over 0. Cosine of theta over sine of theta. And 1 over 0 is undefined. Likewise, if you have the cotangent of the angle theta, that would be cosine of theta, which is -1, over sine of theta, which is 0. And again, -1 over 0, that's undefined. So we're going to have 2 places where our function's undefined, 0 and pi. Well, actually, 0 and pi, and 2 pi, and 3 pi, and 4 pi, and 5 pi, and so forth and so on. But on the unit circle, these are the 2 of interest to us, 0 and pi. You'll find that those will also behave as asymptotes. You'll have one vertical asymptote at theta is equal to 0. And you'll have another vertical asymptote at theta is equal to pi. And of course, you'll have another one at 2 pi and 3 pi and 4 pi. And also negative pi, -2 pi, -3 pi, and so forth. But for our central period, we're going to be using these 2. All right? We can have a few values here. We have 0. Well, that's undefined, right? So that's undefined. Can't do that. But we can do pi over 4. And the cotangent of pi over 4 is the cosine of pi over 4 divided by the sine of pi over 4. But looking on our unit circle, those are the same number. Cosine of pi over 4 and sine of pi over 4 are both root 2 over 2. And if you take a number and divide it into itself, you just get the number 1. So at pi over 4, 0, pi over 4, pi over 2, 3, pi over 4. At pi over 4, the cotangent has a value of 1. So we have that point there. If we use pi over 2, well, again, that's the cosine of pi over 2 divided by the sine of pi over 2. Oh, well, the cosine of pi over 2 is 0. And the sine of pi over 2 is 1. So that's going to be 0 over 1, which is just 0. So at pi over 2, you're going to be on your axis. Here's theta, and here's cotangent of theta. If we use 3 pi over 4, well, then that's going to be the cotangent of 3 pi over 4, which is negative root 2 over 2, divided by the sine of 3 pi over 4, which is positive root 2 over 2. And here these 2 numbers divide out. Oh, but there's a negative left over. So that's going to give us -1. So if you have a theta value of 3 pi over 4, your cotangent will end up being -1. So again, it's going to pass through these points, and it's going to treat these lines as asymptotes. So it'll look something like this. Notice it looks an awful lot like the tangent function, but shifted over a bit and then upside down. Right? If you imagine taking this one and sliding it over a bit and then flipping it upside down, it would look like this. And there we go. So these are the graphs of the central periods of the tangent function and the cotangent function. Once again, this is the central period. Okay. The central periods of the cotangent and the tangent functions can highlight the domain and range of our function. Notice that the domain of this function isn't just limited between here and here. It does go on forever. but it does have regular exceptions. There are regular places where your tangent function is undefined. Likewise, your cotangent function is not just defined between 0 and pi. It'll keep going forever and ever and ever. It'll have different periods between each pair of asymptotes. But you'll also note that you have regular values where your cotangent is undefined, or in other words, regular places where your domain, which are excluded from your domain. Also note that this does go up forever following that asymptote, and this does go down forever, same as this one, which means that even though the domains have some restrictions, the ranges do not. The range for these functions is from negative infinity to infinity for both. So let's go ahead and summarize the things that these graphs have taught us. The tangent function, let's go ahead and write it as a function. So let's say f of theta is equal to the tangent of theta. It has a domain that is all real numbers except where you can find the asymptotes. So this will be, it would be difficult to write it in interval notation because I would have to write it literally an infinite number of intervals. So instead we'll be using set builder notation. If you're not familiar with that, let's take a look at how that works. Set builder notation, we're going to write it as a set, and we're going to say the set of what? Well, the set of x values, right? After all, domain is all your x values. I guess I should say theta, right? Because after all, these are theta values. So the domain is a set of thetas. Okay, well, what thetas? Well, they're the thetas that meet the following criteria. You can have either a semicolon or in some books they'll have a vertical bar. Either one means the same thing. It's the set of thetas that meet the following criteria. We want theta to not equal a particular set of numbers. So it's any theta except for the ones that equal this, 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 and this. Now, again, I don't want to write them individually. That would take literally forever, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It keeps going forever. This would literally take forever. So instead of writing them one at a time, we're going to describe them. Notice this is 1 pi over 2. This is 3 pi over 2. The next one would be 5 pi over 2. Notice that the pi over 2 part is common. 1 pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2. The pi over 2 part is common. Okay, so pi over 2. But then the part that isn't common, we need to describe that. Well, it's 1, 3, 5, 7, 9. Those are all odd numbers. Whenever you describe an odd number, well, to describe an even number, you take something that is multiplied by 2. So 2n would be an even number. Pick any number you like, 17, and double it. Oh, that's an even number because it's the double of something. Oh, but then that would make these even numbers. I don't want even numbers. I want odd numbers. Oh, okay, well, every even number, if you just add 1 to it, it gives you an odd number. If you have the even number 24 and add 1, it gives you 25, which is odd. If you have the even number 60, if you add 1, that's 61, which is odd. So 2n plus 1 is a generic way of describing odd numbers. Right? So this is true for any integer n. So if n is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or also negative 1, negative 2, negative 3, any integer. For any integer n. So this is the domain of the function f of theta equals tangent of theta. It's every theta except for the ones that meet this criteria. They're an odd number times pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, and so forth. The range is just every number. It goes up forever, goes down forever. That one we can just write in interval notation. Note that the period of the tangent function is different from the period of sine and cosine. The period of sine and cosine was 2 pi. Right? They both started at 0 and ended at 2 pi. But this one starts at negative pi over 2 and ends at positive pi over 2. The distance from here to here is pi over 2. The distance from here to here is another pi over 2. So add those together, that's 2 pi over 2. Or in other words, just pi. So here, the period of this is going to be pi. There is one other thing to note. When we were looking at sine and cosine graphs, we had a period, and we had an amplitude. It doesn't make sense to talk about the amplitude of a tangent function, though, because amplitude tells you the distance from the mid-level up, or conversely from the mid-level down. If you have a sine function which has an amplitude of 5, then from the baseline, from the place where the axis is, you would go 5 units up to get to the maximum and 5 units down to get to the minimum. That's what the amplitude means. But for a tangent function, this goes up forever. It goes down forever. So there is no maximum or minimum. So here, note that although the period is pi, here the tangent function has no amplitude. No max or min. There is no maximum or minimum value for the tangent of theta, which implies that there is no amplitude. Not that the amplitude is 0, just there isn't one. It doesn't make sense to talk about amplitudes. The cotangent function works the same way. Oh, I forgot one last thing. We said sine and cosine are even function. Sine is an odd function and cosine is an even function. Here, note that if I have a positive value, I get a positive tangent. If I have a negative value, I get the exact opposite. So if I plug in theta and I get tangent of theta, if I plug in negative theta, I get negative tangent of theta. From the graph, you can tell that these are symmetric with respect to the origin. Either way, that tells us that the tangent function is odd. The tangent of theta, if I take the negative of that, that's the same as if I took the tangent of theta and took the negative of the argument. All right, if I have this argument, this angle, and I get this tangent, if I take the negative of the angle, that's the same as if I took the negative of the tangent. I took this result and took its negative. So the negative tangent of theta is equal to the tangent of negative theta, which implies that tangent is an odd function. Tangent of theta is an odd function. The cotangent function has got pretty much the same thing. In fact, you can describe everything about it exactly the same except for the location of the asymptotes. So here, if f of theta is equal to the cotangent of theta, almost all of this will be the same. The range is still exactly the same, from negative infinity to infinity. It goes up forever, it goes down forever. The period from 0 to pi, okay, that's got a length of pi. It has no max or min, since it goes up forever and goes down forever. So that means that there's no such thing as an amplitude for a cotangent function, just like with a tangent function. This is also true. If you take the negative cotangent of an angle theta, that's equal to the cotangent of negative of theta. Because after all, it's just the reciprocal of the tangent function. And if it's true for tangent, it'll be true for its reciprocal. Reciprocating a number doesn't change its sign. So that implies that the cotangent, just like the tangent, is an odd function. The only difference between this one and this one is going to be the domain. Because with the tangent function, the asymptotes are at negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so forth. However, here, they're a little bit easier to describe. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, and so forth. So here the domain is all values of theta, such that theta is not equal to some multiple of pi, right? 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi, and so forth. So here, that's just literally any integer. So we're going to describe that as n times pi, where n is an integer. Pick any integer you like, 17, plug it in right there, and that'll tell you the location of one of the asymptotes. Any integer you like, negative 4. Okay, negative 4 pi, that's the location of another asymptote. So now, with these properties of the tangent and cotangent function, along with these graphs of the central periods, let's go ahead and see how we can modify these, how we can use our transformations to graph other tangent and cotangent functions with modifications to either the argument or to the outside. All right? So, for example, let's start off by graphing f of theta is equal to the tangent of, let's say, 1/2 theta. And I'll put that in parentheses. Whenever you have just tangent of theta, again, it's okay to just write tangent of theta like I did over here, tan theta. But whenever this is anything more than just a single character, generally we put the whole thing in parentheses, because if you don't, what does that mean? Is that tangent of 1/2 and that's the coefficient of theta? Or is it tangent of the whole thing? It becomes even more complicated if I put a number out here. Let's say plus pi. What does that mean? Is that tangent of that whole thing? Or is that tangent of just this part and then separately I should add pi? Or is that just tangent of 1/2? That's the coefficient of theta and then I'm adding pi. What does that mean? Which of these go together? So whenever you have anything more than just a single character after your tangent, whenever you have something more than just tangent of theta or tangent of x, we use parentheses to make absolutely certain there's no ambiguity. If there is any ambiguity, well, then you start to do things incorrectly just because we don't know exactly what we're talking about. All right, so let's take a look at this one. Just like with the tangent and just like with the sine and the cosine function, the tangent and the cotangent functions have a central period that we're going to be manipulating. Unlike sine and cosine, the tangent and the cotangent don't have a beginning and an ending point, but the asymptotes will serve that purpose. So here what we're going to do is we're going to say, okay, instead of asking where does the period begin and where does the period end, what we're going to do is we're going to ask where is the left asymptote and where is the right asymptote. Once we know where those are, we fit everything else in between there. Okay, so the left asymptote for a tangent function is normally when the argument is at negative pi over 2. Okay, well, our argument may have changed, but it should still have the stuff in the parentheses be negative pi over 2. So the left asymptote is where this argument, 1/2 theta, is equal to pi over 2. Oh, sorry, that should be negative pi over 2. And now we can solve for theta. Let's double both sides. And now we're left with 1 theta is equal to negative pi. The right asymptote will exist wherever the argument, 1/2 of theta, is equal to positive pi over 2. Because again, on the central period, that's where our rightmost asymptote is, at pi over 2. So solving for theta, we can double both sides. And that'll give us theta equals to pi. Okay, so we can take this and we can graph, because now we know where the left and the rightmost asymptotes are. So let's begin by graphing the left asymptote and the right asymptote to give us our domain for our central period. Now here, let me go ahead and actually graph the original function without any modification. Let me just go ahead and graph the tangent of theta. I'm just going to copy this one down again. So without any modification, the tangent of theta should be between negative pi over 2 and positive pi over 2. It should meet the x-axis at the origin, halfway between the origin and the right asymptote, which would be right here. The tangent is going to equal to 1. And halfway between the left asymptote and the origin, the tangent value should be negative 1. Okay, and then you're going to follow the asymptotes in both directions. So this is the graph of f of theta equals the tangent of theta. So now let's compare that to f of theta equals tangent of 1/2 theta. Okay, well, these are my new asymptotes. So instead of having them there, they should now exist over here at negative pi and over here at positive pi. Okay, so just like with our previous examples in the last sections with sine and cosine, whenever you have a number inside the argument, what it does is it dilates things this way. It changes the period. Take pi and divide it by this number, and that'll give you the new period. All right? For sine and cosine, it was 2 pi divided by that number because 2 pi was the period length of sine and cosine. But since the period length of tangent is 1 pi, that tells us that the period length is going to be given by pi, which is the period length of an unmodified tangent central period, divided by b, which is that number there. So for our case, that's going to be pi over 1/2. Dividing by a half is the same as multiplying by 2, so that'll give us 2 pi. And sure enough, look, the distance between here and here, that's 1 pi plus another pi is 2 pi all the way across. All right? So for sine and cosine, this would be 2 pi over b, but since tangent has a shorter period, you use pi over b. It's whatever the original period was divided by that value b. All right, so now we know our asymptotes, but what about the rest? Well, again, halfway between these, you should be at the axis. Now, halfway between that point on the axis and the rightmost asymptote, your tangent should be at 1. Okay, well, halfway between here and here is pi over 2, so tangent of that value should be 1. And halfway between the left asymptote and this point on the axis, which is negative pi over 2, my tangent value should be negative 1, right there. So even though these red lines served as an asymptote to the original function, they don't serve as an asymptote to the new function. These do. So we're going to have our graph follow these, go through these points and follow the asymptotes, the new ones. And there we go. We have our graph. It still looks the same. It's got the same shape, but everything's been stretched out a bit. All right. Let's take a look at another example. I'm going to go ahead and put it on the same graph here just to compare the values and the graphs they're in. So the next example, let's go ahead and graph f of theta is equal to 2 times the tangent of theta. Okay, now this one is, at first, it's going to seem rather simple. You're just going to multiply the whole thing by the number 2, which means you're going to, just like with a sine and a cosine function, you're going to just change the magnitude, change the amplitude. Well, yeah, but then you remember tangent doesn't have an amplitude. It goes up forever. So then that won't work. Well, it does. You just have to be careful with what you mean by you're doubling the amplitude. Because here, it's true, there is no maximum. It goes up forever. And if it goes up forever, you can't make it twice as high, right? You can't have double forever. Same thing in the other direction. But that doesn't mean anything about the points in between. All right? This goes up forever, but I still have points in between that don't go up forever, that have fixed values. So here what I can say is, okay, at this point in the middle, the tangent of 0 is 0. And if I double 0, okay, well, that's still 0. That doesn't change anything. But what about this point? At pi over 4, the tangent is 1. But if I double that, well, now it's 2. So whereas this number would change the maximum and minimum of sine and cosine, since tangent doesn't have a maximum or a minimum, we're going to have to modify that slightly by saying, okay, we're not looking at a maximum or minimum. What we're doing is we're looking at this quarter point and this 3/4 point. The one in the middle is 0, and, well, anything times 0 stays 0. So this one won't be affected. But here, this point has a tangent value of 1. So doubling it gives you tangent of that value is 2. Likewise, this value of theta has a tangent of -1. So doubling it will give you a value of -2. It's still going to follow the asymptote, so it's still going to go up forever and down forever. Rather, it's the points in between that become affected. Just like that. So here, and I'm going to go ahead and put this in quotes because, again, technically it's not an amplitude since tangent doesn't have one. But let's say, amplitude does not affect the max and min, the maximum and the minimum, because tangent of theta doesn't have one, doesn't have any. But what it does do is it affects the points in the middle. The quarter point and the 3/4 point are the ones you want to focus on. Instead, focus on the point 1/4 on the points 1/4 and 3/4 of the way through the period. Just like that. So now let's take a look at an example where we start combining some stuff. Let's use cotangent this time. So for example, let's go ahead and graph the function f of theta is equal to, let's say, 2 cotangent of let's say pi over 2 theta minus pi over 2. Actually, let's just say minus pi. That should be okay. Plus 1. All right, so let's go ahead and do that. All right, order of operations tells us to focus on parentheses first, and that's going to be a good idea whenever we graph any trig function. If there's anything in here, we should take care of that first. As we saw before, whenever you change your argument, it's going to change the location of your asymptotes. Now notice here, these asymptotes are going to be different. For tangent, they're at negative pi over 2 and positive pi over 2. But for cotangent, they'll be at 0 and at pi. So let's go ahead and take a look at the left asymptote. And the left asymptote will move to correspond to the argument being equal to 0. All right, so pi over 2 times theta minus pi is equal to 0. And we can solve for theta here. Let's add pi to both sides. That goes away. And we're left with pi over 2. Theta is equal to pi. Okay. Now, we can go ahead and multiply both sides by 2 over pi. Multiplying by the reciprocal, the 2's will divide away, the pi's will divide away, leaving me just theta. And same thing over here. Here, pi divides pi, and I'm left with a nice simple number. Theta is equal to 2. Just like that. We can now see what happens to our right asymptote. The right asymptote will be wherever the argument, in this case pi over 2 times theta minus pi, is going to equal to pi. For the cotangent function, the central period has asymptotes at 0 and at pi. So 0 and pi. Now we can solve for theta to see where our new asymptote is going to be. So let's add pi to both sides. And that's going to give us 2 pi there. So pi over 2 times theta equals 2 pi. And now we can go ahead and multiply both sides by 2 over pi. And again, that's so that 2 divides 2 and pi divides pi. Here, pi divides pi as well, but these don't divide out. 2 times 2 is going to give us theta equals 4. And this is our new set of asymptotes. All right, so let's go ahead and place these on the graph and see what happens to our cotangent function. All right, so now theta is equal to 2 and theta is equal to 4. That's going to be the location of our new asymptotes. All right, so the left one is over here. And the right one is over here. Okay, now the next part I'm going to go ahead and just draw in pencil for now because I'm going to go ahead and move things in a moment. Note that normally what would happen is, okay, if these things out here didn't exist, this stuff in the argument would now tell me, okay, here are my new asymptotes. Now just draw your cotangent function. Your cotangent function, halfway in between the asymptotes, you're going to be on the axis. Halfway between there, you'll be at 1, and halfway between those two, you'll be at -1. Okay, so halfway between 2 and 4 is 3. So I should be at the point 3, comma 0. That'll be where I'm at the axis. And now halfway between 2 and 3, which is what, 2.5, 2.5, I should be up here at 1. And then halfway between 3 and 4, which is 3.5, I should be down here at -1. And then I'd have a graph that looks like that. Well, yeah, but what about these? These are going to modify things. Well, remember what this does. This changes your amplitude. Well, yeah, but we don't have an amplitude for tangent and cotangent. Well, sure, in that we can't modify a maximum and minimum because they don't exist. But what we can focus on are points that we do have. In this case, oh, if that theta value, 2.5, gives me a cotangent value of 1, doubling it will give me a cotangent value of 2. And likewise here, if at 3.5 I have a cotangent value of -1, doubling that will give me a cotangent value of -2. So now the whole thing's gotten taller, well, so to speak. All right? It's still going up and down forever, but in between, these points are moving out. They're getting more distant from the axis. Oh, but then what does that +1 do? Well, remember, addition and subtraction outside simply works as a vertical translation. This one, +1, moves everything up by 1. So here, this point goes from 0, 3, I said that backwards, from 3, 0 up to 3, 1. Okay, so now the point should be up here. Goes up 1 step. This started at 2.5, comma 1, but then we doubled it to 2.5, comma 2, and then everything moves up 1 step to be at 2.5, comma 3. And then this point down here also moves up 1, just like that. So we took our tangent function, we stretched it out, and then once it was stretched out, we moved it up by 1. And now we go ahead and redraw the graph. It's got to still have that same shape, right? It hasn't changed what kind of function it is. It's just changed some of the details. So let me go ahead and erase this one. And let me go ahead and draw my cotangent function. Remember the shape of the cotangent function? It's like the tangent function, but upside down. It'll go up this way and down this way. So from here, it's going to go up this way, following the asymptote. Don't cross the asymptote. That's the point of having an asymptote. And then over here, it's going to come down this way. And again, don't cross the asymptote. And this is the graph of our function f of theta is equal to 2 times the cotangent of pi over 2 theta minus pi plus 1. You'll recall that the secant function is defined is the reciprocal of the cosine function, and that the cosecant function is defined as the reciprocal of the sine function. So in order to talk about their graphs, we're going to start by looking at the original graph of sine and cosine, or at least the central periods thereof. So here we have a graph of f of theta is equal to the sine of theta. Okay. All right, so if I'm trying to graph the cosecant function, it's going to be the reciprocal of these values here. All right, well, what are the reciprocals of these values? All right, well, let's see. Let's say I want to graph f of theta is equal to the cosecant of theta. And recall that's equal to 1 over the sine of theta. It's the reciprocal of these values that we have from before. Okay, so if theta is equal to 0, well, then that means that the sine of theta is also equal to 0. Right? There's a point 0, 0. Okay, but if I'm trying to take the reciprocal, that would be 1 over 0, which is undefined. And as we saw for the secant, tangent and the cotangent functions, whenever your function is undefined, we're going to end up with an asymptote. So here, wherever this is equal to 0, its reciprocal is undefined. So here, let me go ahead and draw this line here. Our graph will never touch this line, although it will come near it. Likewise, when theta is equal to pi, and when theta is equal to 2 pi, the sine of theta equals to 0. And so, 1 over the sine of theta would also be undefined. The reciprocal of 0 would be 1 over 0, which means it's undefined. There and there. Okay, but those are the only places in the central period of the sine function where the sine of theta is equal to 0, which means all these other values are going to have valid reciprocals. For example, this point right here, when theta is equal to pi over 2, the sine of theta is 1. Okay, well then the cosecant of theta would be the reciprocal of that. Well, the reciprocal of 1 is still 1, so that point remains the same. But now, what happens as I move away from that point? For example, here, there is a point where if I take the sine of that point, I'm going to get 1/2. In fact, there's two of them. Right here, I'd have pi over 6, and over here, I'd have 5 pi over 6. So between here and here, between these two asymptotes, there are two places where the sine of theta is equal to 1/2, namely the sine of pi over 6 is 1/2, and the sine of 5 pi over 6 is 1/2. Okay, so if the sine of pi over 6 is 1/2, then the cosecant of pi over 6 must be the reciprocal of 1/2. Well, the reciprocal of 1/2 is the number 2. So here, if I use this angle theta, sine of theta would be here. Cosecant of theta would be right here. That would be at 2. And likewise for this one. If the sine of 5 pi over 6 is 1/2, then the cosecant of 5 pi over 6 would be 1 over 1/2. Or in other words, it would be 2. So notice that my graph is going in the opposite direction. Whereas over here, this was the maximum. It looks like that's the minimum for this part. It's going to start from here and go up from there. Okay, so notice as your sine of theta gets smaller, the reciprocal is going to get larger. And in fact, because we have an asymptote here, it's going to keep growing up along the asymptote there, and same thing for this asymptote over here. And there we go. Well, that's not quite the end of it, because what about over here? All of these values are negative. The reciprocal of +1 is +1. What's the reciprocal of -1? Well, it's still -1. So this value stays where it is. The sine of 3 pi over 2 is -1. The cosecant of 3 pi over 2 is going to be the reciprocal of -1. Well, that's still -1. But then, just like over here, as the sine of theta moves closer to 0, the cosecant of theta will grow larger and larger and larger. The reciprocal of a small number is a large number, so the reciprocal of very small numbers are very large numbers. Oh yeah, but the reciprocal of negative numbers are still negative. Okay, so it's going to grow, but in the negative direction. So the graph will look something like this. These two together give us one period of the cosecant function. Notice that unlike our tangent and cotangent, here the full period rests between two sets of asymptotes, not just one. For a tangent or a cotangent, between a pair of asymptotes, that's one period. But for a secant function, it's here's one part, here's another part of one period. Note that that means that the period begins at 0 and it ends at 2 pi. So just like with sine, I have a period of 2 pi, just like we had with sine of theta. Note here that your asymptotes are at 0, pi, 2 pi, 3 pi, 4 pi, just like with the cotangent function. which means that the domain of this cosecant function is all real numbers, except for 0 and pi and 2 pi and 3 pi and so forth. So the domain, just like with the cotangent function, we're going to write it in set builder notation. The domain is all thetas such that theta is not equal to one of these. Oh, well, what are these? Well, these are just integers times pi. 0 times pi, 1 times pi, 2 times pi, and so forth and so on. So this is n times pi, where n is any integer. The range of this function, well, notice this goes up forever and down forever. So you might think, oh, from negative infinity to infinity, just like tangent and cotangent. Well, not quite. Notice that right here, your function doesn't exist between -1 and 1. The function goes from 1 up forever, and it goes from -1 down forever. But between -1 and 1, I don't have anything for cosecant right here. So my range is going to be everything from negative infinity up to -1, union with everything from 1 to infinity. Here we're going to include -1 and +1 because notice those are points on our function. Just like that. So that's the range of our secant function. Of our cosecant function. The secant function we're going to treat the same way. Notice this is one period of the cosine function. Okay. Here, I'm going to do the following. Normally, when we talk about the central period of the cosine function, we talk about this part from 0 to 2 pi. But just for the purposes of this reciprocation, we're going to go ahead and talk about the period starting from -pi/2 up to 3 pi. Okay, so here we're not going to worry about this part. We're going to consider one period from here to here. You say, well, why is that? Well, notice if we do this the same way, we're going to have an asymptote wherever this meets the axis. Wherever the function is equal to 0, its reciprocal will be undefined. Okay, so I'd have an asymptote here, and I'd have an asymptote here. Okay, now notice that the maximum of one curve becomes the minimum of its reciprocal. So here's a maximum, and if I reciprocated it, that would become a minimum going up this way. Same thing over here, it would go up this way. And then just like this one, this minimum becomes a maximum of this portion. You say, well, what's wrong with that? Well, the problem with this is that this is sort of disconnected. Right here, you have one part of our graph that's sort of been split in half. Looks like half of it's over here and the other half is over here. But if instead of thinking of my period as going from 0 to 2 pi, if I just start from back here and ignore this one, well, now I can say, oh, well, now let me just use this as an asymptote instead. And now I keep this all together. Instead of having one piece here and one piece over here, we can just keep it all together. So it's actually a matter of choice. Some textbooks and some people actually prefer to do that. They'll say, you know what, let me just go from 0 to 2 pi. And then my secant graph will look like that, that, and that. And there is technically nothing wrong with doing that. But another choice that can be made is to keep it all together. Right? So here, that's the choice we're going to go with. We're going to say, okay, consider the period of cosine that goes from -pi/2 to 3 pi/2. Wherever that hits the axis, that's where our asymptote is going to be. So -pi/2, +pi/2, and +3 pi/2. The reciprocal of 1 is still 1, and from there it goes up, joining the asymptotes, along the asymptotes. The reciprocal of -1 is still -1, and from there it goes downwards along the asymptotes. Okay. Note that this one in blue is f of theta is equal to the cosine of theta. And we didn't take the typical central period of cosine of theta. We took a slightly different period. But that's just to make this one put this one all together so it's not disconnected. All right, so if that f of theta is cosine of theta in blue, then our f of theta in red, f of theta is equal to the reciprocal of the cosine function, which is the secant of theta. Okay. Note that the period, even though we've shifted it over a little bit, it's still got the same length, right? That's length 2 pi. If we shift it over, it's still got the same length. So the period of the secant function is the same as the period of the cosecant function, which is the same as the period of the sine of the cosine function, 2 pi. We have 6 trigonometric functions. Tangent and cotangent have a period of pi. All the others have a period of 2 pi. The domain of this one is all real numbers except for these asymptotes. You notice these asymptotes are in the same place as the asymptotes of tangent, right? At negative pi over 2, at pi over 2, 3 pi over 2, 5 pi over 2, and so forth. So the domain of this one will look the same as the domain of the tangent function. It's going to be all thetas, such that theta is not equal to some odd number times pi over 2, 1 times pi over 2, 3 times pi over 2, 5 times pi over 2, and so forth. So that would be 2n plus 1 pi over 2. Okay? That's a generic way of writing odd numbers. 2n is even. So adding 1 to an even number makes it odd. So this is a generic way of writing an odd number. So odd number times pi over 2. Yeah, 1 pi over 2, 3 pi over 2, 5 pi over 2, and so forth and so on. Where, again, n is any integer. Where n is any integer. And the domain is the same as the domain of the cosecant function. It goes up forever and down forever, but you're missing anything between -1 and 1. So the range of the secant function is the same as the range of the cosecant function. It's everything except for the stuff between -1 and 1, which we can write in interval notation from -infinity to -1, union with 1 to infinity, just like that. And these are the graphs of one period of the cosecant function and the secant function. We can use this information to graph any modifications of these as well. So if we want to graph secant of theta, well, that's this one. But if we want to graph secant of 2 theta plus pi over 4, or any variation thereof, we can use this information to do that. Okay? So let's see how that works. Let's consider a problem. All right. For example, let's graph f of theta is equal to 2 times the secant of 1/2 x plus pi over 4. All right, just like that. All right, we're going to graph this. But what we're going to do is we're going to begin by graphing 2 times the cosine of 1/2 x plus pi over 4. The reason for that is because cosine is something we already know how to graph. But once we graph cosine, the zeros of the cosine graph, the place where it crosses the axis, that'll tell us where our asymptotes need to be. And once we know where our asymptotes are, that'll give us the shape of the entire graph. So generally speaking, whenever you're going to graph a secant function, you start by graphing the cosine function and then use that to graph your secant. Likewise, if you want to graph a cosecant function, you start off by graphing a sine function and then use that graph to find the reciprocal function, the cosecant function. So here we're going to say, okay, let's start by graphing, let's give this a different name. Let's call this g of theta is equal to 2 times the cosine, and again, cosine and secant are reciprocals, that's why we're using this one, 2 times the cosine of 1/2 x plus pi over 4. Okay, well, we know how to graph that. We're going to begin by taking this argument and using it to find where one period of cosine begins and where it ends. And we'll do that by taking that argument and setting it equal to 0 and 2 pi respectively. So one period of g of theta begins whenever 1/2 x plus pi over 4 is equal to 0. 1/2 x plus pi over 4 is equal to 0. We can go ahead and subtract pi over 4 over to the other side. So that's 1/2 x is equal to negative pi over 4. Now go ahead and double both sides, multiply both sides by 2, and that'll give us x is equal to negative 2 pi over 4, and the 2 over 4 can reduce to be 1 over 2. So that's negative 1 pi over 2. So our period of g of theta will begin, these should all be thetas, shouldn't they? Let me be consistent. You can use x if you like, and in fact our textbook, some of the problems do use x. But here I started with theta, so I should stick with theta throughout the problem, shouldn't I? My apologies. There we go. Now let's be consistent. All right, one period of g of theta begins when theta is equal to negative pi over 2, and it ends whenever the argument 1/2 theta plus pi over 4 is equal to 2 pi. All right, from 0 to 2 pi. All right, let's subtract pi over 4 over to this side. 2 pi minus pi over 4. All right, that'll be 7 pi over 4. All right, 8 pi over 4 minus pi over 4 is 7 pi over 4. And now we'll double both sides. So that'll give us theta is equal to, if we double that side, that's 14 pi over 4. 14 over 4 can reduce to 7 over 2. So that's 7 pi over 2. And there we go. We now know the beginning and the ending of one period of a function. Here, this is just going to tell you the amplitude. So when we graph it, it'll start here and end here, and we'll know the amplitude. All right, so let's go ahead and take that, and we'll go ahead and graph that. So let's look at where our graph should begin and where it should end. Here we note that at theta equals negative pi over 2, that's where our period of our cosine function should begin, and it should end way over here at 7 pi over 2. Okay, so it's a lot longer than usual, right? Usually cosine starts at 0 and ends at 2 pi, but now it starts back here and ends out here. All right. So here, let's go ahead and actually graph what the normal cosine function usually looks like. It usually starts at a maximum, right? And then it hits the axis when theta is equal to pi over 2. Then it hits a minimum when theta is equal to pi. Then back to the axis at 3 pi over 2, and then back to the maximum when theta is equal to 2 pi. So that's what our central period of cosine usually looks like. Okay, but now we've stretched it out a bit. It's going to start all the way back here, and it's going to end all the way out here. Not only that, but our amplitude has changed. That value is 2. So now instead of going up to 1, now it should go up to 2. Okay, so let's go ahead and do that. We have, instead of starting at theta is equal to 0, we're going to start at theta is equal to negative pi over 2. We're going to start at the maximum, and because the amplitude is 2, the maximum is now twice as high as it otherwise would have been. So we're going to start there, and we're going to end, instead of ending when theta is equal to 2 pi, we'll end when theta is equal to 7 pi over 2. We're supposed to end at a maximum, and again, the maximum, because the amplitude has changed, should now be twice as high as it was before. So right there, okay. Halfway between these two, halfway between 7 pi over 2 and negative pi over 2 is 3 pi over 2. Right? That should be your minimum. Halfway in between your maximums is your minimum for any cosine period, right? For the central period. Okay, so 3 pi over 2. Normally my minimum's at negative 1, but again, we've changed the amplitude, so that's going to be down here at negative 2. The amplitude is twice as big, meaning the maximums and the minimums are twice as big as before. And then your graph is supposed to hit the axis halfway between the maximum and the minimum. Notice here and here, halfway between the maximum and the minimum, that's where you hit your axis. Okay, well here's your maximum and your minimum. Halfway in between that is, well, it's actually still right there. That's kind of a coincidence. It doesn't usually happen like that, but that's what happens for this example. Halfway between negative pi over 2 and 3 pi over 2 is pi over 2. If you're not sure how I did that, it's the average. If you add these two together, 3 pi over 2 plus negative pi over 2, 3 pi minus 1 pi is 2 pi over 2. And 2 pi over 2 is just the same as saying pi. So the sum of these two is pi. But now, to find the average, you add them together and divide by 2. So when you add them, that's pi. And then divide by 2, well, that's pi over 2. Over here, this is going to hit the axis again between, again, that maximum and that minimum. All right, we're going to find the average of these two numbers. 3 pi plus 7 pi, that's 10 pi over 2. All right, if you add these together, that's 10 pi over 2, which is just 5 pi. But now, to find the average of these two, add them together, gives you 5 pi, and then divide by 2. Okay, so 5 pi over 2. There we go. So halfway between those, we find this. All right, so now we can connect our dots. It's still going to have the same pattern. It's going to go from a maximum through the axis to a minimum, through the axis back up to the maximum. All right, and that's the graph of g of theta is equal to the cosine, that should be double the cosine, because we changed the amplitude, double the cosine of 1/2 theta plus pi over 4. But now we can use this information to find the graph that we wanted, which was double the secant of 1/2 theta plus pi over 4. And the way we're going to do that is the way we found the graph of the central period of secant using the central period of cosine. Okay, this is where you cross the axis. Okay, so that's going to be where I have an asymptote. And that's going to be where I have an asymptote. Okay, the reciprocal of negative, so right here, the minimum is going to become the maximum of this part here. Wherever I have the minimum of the original function, that's going to be the maximum of this portion of the reciprocal function. So here we're going to take this and we're going to say from here we're going to go down and we're going to go down. Remember, you're following your asymptotes. Don't touch those. So just like that. Okay, and then again over here there is sort of a style choice. Some people would say, okay, from here I can go up and from here I can go up. However, the way this textbook does it, if you look up the answers in the homework and such, the way they do it is as follows. They'll go ahead and say, okay, you know what? Go ahead and sort of kind of copy and paste. Imagine this thing is over here. So right here, this goes from 5 pi over 2 to 7 pi over 2, right? Okay, well, the distance between here and here is pi. Okay, so just make up the difference back over here. So this will be, let's see. This will be like this. Basically just, we're going to take this part. It's 2 spaces forward from 5 pi over 2 to 7 pi over 2. So here we'll go 2 steps in this direction. That'll bring us back to negative 3 pi over 2. Basically, I'm going to say cut and paste. Something like that. All right. And so here's where you hit your axis. So this will be where your other asymptote lies. Just like that. And so here, this is the maximum of this part of your cosine graph. So it'll be the minimum of this part of your reciprocal function, your secant graph. And there we go. This part in red gives us the function that we wanted. Note that the asymptotes are not part of the graph, but they are usually drawn in anyway to help guide the shape of our graph. So this stuff in red from negative 3 pi over 2 up to 5 pi over 2 is going to be the graph of f of theta is equal to double the secant of 1/2 theta plus pi over 4. And there we go. Note that when we graph a secant function, and it'll be the same thing for a cosecant function, the secant and the cosecant are practically an afterthought. what we do is we spend the entire time accurately graphing the cosine function, or in the case of a cosecant function, we'll start by graphing the sine function. And then once that one is accurately drawn, we simply say, okay, where does that hit the axis? That's where our asymptotes are going to be. The maximum of one part becomes the minimum of the reciprocal function. The minimum of this part becomes the maximum of the reciprocal function. You kind of flip it out the other way. And don't forget to follow your asymptotes. Your graph should never cross those. And that's it. So go ahead and give this a try. Again, you start by graphing either the sine or the cosine function as appropriate. And once you have that one accurately drawn out, then you worry about finding the reciprocal function. You use this one to find this one. So go ahead and give that a try. Go ahead and graph the function f of theta is equal to, let's see. Let's make this one negative. Let's make this one negative cosecant of x plus pi over 2. Let's make that minus x minus pi over 2, just because that one was already plus, so let's make one look a little different. X minus pi over 2, and then plus 1. Okay, so go ahead and give that a try. Begin by considering the graph of the function negative sine of x minus pi over 2 plus 1. And then from there, use that graph to find the graph that we want. Go ahead and pause the video and create your graph. And once you have created that graph, go ahead and unpause the video and we'll go through it together. All right, so let's take a look at this one. So let's begin by graphing g of theta, which is going to be negative the sine of x minus pi over 2 plus 1. All right. I know what a sine function looks like. It starts at the axis, goes up to a maximum, down back to the axis, down to a minimum, and then back up to the axis. And the maximum and the minimum are at 1 and negative 1 respectively. Okay, so here I haven't done any modification. This is just a regular sine of theta. F of theta equals sine of theta. So now let's modify this one. Okay, first of all, I note that I have a change here. This is going to be a phase shift. Now, whenever there's a number here and a number here, you're probably better off taking the argument and setting it equal to 0 to see where you start, setting it equal to 2 pi to see where you end. However, if there is just one number here, it's probably simple enough to just use a transformation. So here I'll do it both ways. One way is to say, well, that's a phase shift of pi over 2. So the whole thing moves to the right, pi over 2. So this point moves this way, this point moves this way, this point moves this way, and the whole thing just shifts over. If you're not comfortable with doing that, of course, you can always do what we've done before and take this argument and set it equal to 0 and 2 pi and see what happens. So if I take x plus, that should be a minus. If I take x minus pi over 2 is equal to 0, I can add pi over 2 to both sides to get x is equal to positive pi over 2. Okay, and then if I take the argument and set it equal to 2 pi, x minus pi over 2 is equal to 2 pi. Again, I can add pi over 2 to both sides. This will be x. 2 pi plus another pi over 2 is 5 pi over 2. Just add this to the other side. So now, either way, whether you noticed, that's a phase shift, I'm moving to the right pi over 2 units, or if you notice that, I can do this the same way I usually do by taking this, setting it equal to 0 and 2 pi and solving. Either way, you notice you get the same result. All right, so here this shifted over. Instead of starting back here, now it starts here. Instead of ending here, now it ends here. All right, so that would go like this. Everything just shifts over a bit. Notice we're not done yet. This is just the next step in the progression. Okay. Now, this negative on the outside causes a reflection. The whole thing flips upside down. So now I have this graph that starts at pi over 2 and it ends at 5 pi over 2, and it's going to flip upside down. So whatever's at the axis stays there. Right? If you reflect around the x-axis, anything that's on the x-axis stays there. But now this maximum comes down here to be a minimum, and this minimum comes up here to be a maximum. So the graph now looks like this. It's upside down. Okay? So it goes from here down, then back up here. Now it's at a maximum, whereas it was at a minimum before, and now you come back down here. And finally, that plus 1, I guess I'm looking at this one here. This plus 1 tells you to move everything up one step. All right, so this goes from here up one step. This goes from here up one step from -1 to 0. Okay. This goes up one step. This goes up one step. And this goes up one step. All right, so you've moved everything so you started from here. You move everything to the right, so now you're here. Then you flip everything upside down, so now you have this wave. And then you move that wave up by 1 to end up with this wave. All right, so that's the graph of g of theta equals negative sine of x minus pi over 2 plus 1. Okay, so now let's go ahead and use that information to find the graph of our function f. So here, let me label this one. This one's g of theta. Over here, I'm not being consistent, am I? These should all be thetas. It doesn't really make a difference what variable you use, but I really should use the same variable throughout. I should not be jumping back and forth between two different variables within the same problem like that. So there we go. So now we have, this is our g of theta. So now we can say, okay, wherever we have this point, and this point, in other words, the points that came from the axis, the fact that they've moved doesn't change anything. They're still the points that started on the axis, and so these are the points that are going to give me my asymptotes. Notice this point isn't on the axis anymore, but that doesn't matter. The fact that this point came from the axis, right, that's what's telling you that this is your asymptote. There, there, and there. Just like that. And now, if this is a maximum of this part of my graph, it's going to become the minimum of the reciprocal of the graph. Just like that. So this will follow the asymptote. Remember, don't cross the asymptotes. It's going to follow along it. If this touches or crosses it, that's incorrect. Same thing over here. This is the minimum of this part of my graph. So between those asymptotes, this now becomes the maximum. And again, don't touch those asymptotes. And there it is. This graph in blue, this point is 2 pi comma 2, going up toward these asymptotes that are at 3 pi over 2 and 5 pi over 2. That's part of my graph. And over here, starting from pi comma 0, and then going down along these asymptotes at pi over 2 and 3 pi over 2, that gives us our graph. So this stuff right here in blue, that's our graph of f of theta. And that's really it. Note that, once again, the graph of the cosecant function, just like up here, the graph of the secant function, is kind of an afterthought. You worry about graphing the cosine function. You graph the sine function. And then once you have those and you put the work and details into those, then you can use that information of the sine function or of the cosine function to then find your asymptotes and then graph the reciprocal function, whether it be the secant or the cosecant function. So for the most part, the important part is, can you graph a cosine and a sine function? If you can do that, this is just one step on top of that. And that's it for this section. So if anybody has any questions, comments, or problems, please make a note of those and reach out during office hours during our next session. And I hope everyone has a nice day.